David Landler. We're very happy to have him here from Berkeley. He's going to tell us about applications of arboreal singularities.
Great. Thank you very much to the organizers. Congratulations on the grant. So let me just first start by apologizing to those of you who crossed paths with me recently, because I've probably told you about this, and I'm going to tell it to you again. So, but I'm going to try to get more towards applications, certainly during this talk. Okay, so let me remind you of a kind of starting point that appeared in Maxime's first talk. So Kontsevich made the suggestion that we should study exact symplectic manifolds. The exact symplectic manifolds, M omega, by choosing a Lagrangian skeleton. Okay, so omega is differential of some alpha by choosing a Lagrangian skeleton. And I'm going to do lots of examples of Lagrangian skeleton. So I'm not going to try to formalize this into a specific, into a precise definition, but I hope you'll see it. You'll recognize it when I say it. Okay, so let me just make a comment, because I may shift contexts a bit during the talk, which is to say that this is equivalent to a slightly modified context from contact geometry. So we can also study the contact manifold, where we simply cross with the real line, say, so n equals m cross r, and then we take the contact form, lambda equals alpha plus dt, is that right? Plus or minus dt. And then this Lagrangian skeleton, let's call it lambda inside M, will be something that in particular will be exact, and so will be able to be lifted to a Legendrian subvariety. So we could also study, alternatively, a Legendrian subvariety, I don't know, L inside N. Okay, so these two contexts you can kind of go back and forth between. So at some point, if you hear me saying contact and Legendrian, I simply mean that here we want to be thinking about Lagrangian skeleta always that are conic, meaning there's a Liouville flow given by the exact structure, and well, anyway, that's the equivalent to studying a Legendrian. Okay, so what I'd like to do is start with a kind of a list of examples, and then kind of examples that occur naturally, and then talk about arboreal singularities. Okay, so examples. Okay, so the first example is just n is the cotangent bundle, some base manifold x, and lambda is the zero section. Okay, so this is a useful example. Contains a lot of interesting geometry, and one thing you can say is that if you understand, well, studying the symplectic geometry of M is related to the differential topology of X. Okay, so there are a lot of deep questions still not understood about how much this dictionary really is a precise dictionary. But in any case, these two, I don't know what the right kind of font is to use for something that conveys some relationship here. Okay, so the second example, let's call it 1 prime, is where we keep the symplectic manifold to be T star X, but now we fix a stratification of X. So we have, let's say, S be some stratification, so let's call it Xi. So I is an index set, so this is a stratification. Okay, so kind of a reasonable decomposition of X into submanifolds. And then we can take lambda to be, well, I'll write as T star Sx, which is the union of the conormals to the strata. So T star, a union over I of T star Xi X. Okay. And here, the analog of this kind of relationship, I'd say, is given by the kind of stratified topology of X. So questions you can ask about the stratification have something to do with what people call microlocal geometry. So microlocal means, well, you study the geometry of the manifold, not just locally in the manifold, but actually locally in the cotangent bundle. It comes from PDE. And, well, there's a very rich theory here. We'll eventually talk about microlocal sheaves. And, well, in any case, I'd say these two kind of play a generalization of this. Okay. Maybe I should draw a picture. Yeah, let me draw everyone's favorite picture, which is here. Maybe X is a circle, and then lambda, which is the color shape, lambda is the 0 section. Okay, and then here, say X is a circle again, but now lambda is something like the union of these two pieces. So the symplectic manifold hasn't changed, but the skeleton has, and the way we'll think about the symplectic manifold changes dramatically as well. Okay. So next example, I'm going to do about 2 or 3 more, is a Riemann surface. So let's take M to be a punctured Riemann surface. So punctured Riemann surface. Okay, and then there's a well-known story about what kinds of lambdas you can think about. I'll just say that lambda should be a ribbon graph. So a ribbon graph, of course, sorry, is that? Okay, a ribbon graph. Someone doesn't like ribbon graphs. I'm going to try one more time and I'll take off nodding. What's that? A ribbon skeleton. It's okay, Tony, if I fail or you?
Well,
all right. Let's see if I don't.
Everybody could keep it.
The force is strong right here. Okay.
Try not talking to the blackboard. I think it's reverberating.
Ah, it's reverberating. All right. So talk out of my ear. Okay. That's. I'm gonna take it. Okay, I'll shout. You all can hear me. The mic won't hear me very well, but okay. Is that okay, Tony? All right. So ribbon. Now, if we hear it, we'll know something serious. So ribbon graph. Okay, so of course a ribbon graph covers the Riemann surface, but what I mean here is you should just think of a graph that you draw on the Riemann surface that has all the usual properties that you find from the ribbon graph. So let me draw a picture just so you have something in mind. So maybe you have a couple of punctures, and then you draw some graph which is homotopy equivalent. I don't know how to draw the most interesting thing, but here we go. Okay, so maybe it looks like this, but maybe also it has some spikes that go out, to these punctures. That's fine. I don't know, like that. Anyway, something like this picture. Okay, so that's another kind of example. Yet another example is symplectic resolutions. So M could be a symplectic resolution. So what I have in mind here is this is some kind of affine conic complex Poisson variety. And this is a symplectic resolution. Okay, so the usual typical first examples of this are ADE surface resolutions. And then lambda, well, you have a lot of different choices, as always in this game, what lambda could be. And one typical thing to do is the following. You would take a picture like this. So here's maybe your x, and then above it is x tilde. Okay? And then you might pick some favorite Lagrangian, some favorite conic Lagrangian down here, and then you would look at its inverse image. So if we call this pi, you would look at the inverse image of this and see something like that. So lambda inside x tilde, some conic Lagrangian subvariety. Okay, so so these are all of these situations are very, very rich in and of their own right. The one that I'd like to focus on today, in the part of the applications that I mentioned, are going to be Landau-Ginsburg models. So this audience knows a lot more about Landau-Ginsburg models than I do, but I'd like to just spend a couple of minutes explaining to you how I'm thinking about them in terms of skeleton, okay? Because it may not be completely evident. Okay, so this is the main kind of example for today. So Landau-Ginsburg models. Okay, so there's lots of different generality we can have in mind. Let me have in mind just the generality of M being, say, Cn, and then we have some superpotential W. Okay, and so the picture that we'll draw is, here's the W plane. Okay. And so it's a complex, it's a copy of C, it's just that C up there. And then inside the W plane, there are some critical values. Here are the critical values, and then there's also everything else, which is a regular value, so I'll just pick one regular value here. And then you should have a picture of M as living above this. Okay, so here's W. And what we do is we typically want, well, okay, so there are lots of different ways to set up this story. Typically, one needs to pick some extra data here. And so what I'm going to do is the following. So I'm going to first say that I already know in the fiber above this point, so let's call the fiber above this point, need some pictures. So here's the fiber above this, this general point. So this is, let's call it F, right? F regular. Okay? So inside F regular, I'm going to assume that someone has already given me a Lagrangian skeleton. Okay? So whatever we have in mind, I already have some kind of Lagrangian skeleton. I don't know, I can draw like a curve. I already have some Lagrangian skeleton shows in here. Okay, something that looks like that. Okay. And then we choose a collection of cuts in the plane. So maybe we connect all of these points, all the critical values, we connect them to our favorite regular value, and then we connect our favorite regular value off to, I don't know, positive infinity. So somehow, I don't know why my picture became oriented like this. Maybe it's standard to have it be the positive real direction. Okay. So, so above each of these points, we have some singular fiber. Okay, so that's F singular. Okay, it can differ above these different points. And then what you can do is you can construct a total skeleton in the total space M by parallelly transporting the skeleton that you have and then watching as the vanishing cycles contract. Okay? So this is something everyone in the subject knows how to do if this is a Morse function, right? You have some vanishing spheres and then you cap them off with thimbles. But what I'm asking you to do now is just take whatever limits you get, okay? Even if the original thing is very complicated, and even if these singular points involve more than just a sphere collapsing. Okay, so if these singular points involve a huge amount of geometry collapsing, so be it. Okay? So I can't really, I don't know, draw the picture well, but what you would see here in this cartoon is maybe something like this, and the total Lagrangian, if you think of this path lifted up here would look something like, I don't know how to draw it exactly, but kind of looks sort of like a cone over what you had in the general.
So we assumed your original skeleton and fiber is large enough to include vanishing cycles.
That's right. Oh well. Yes and no. I mean, you can. I mean, that's of course the case where things will be most interesting. If you don't, I mean, I could have said, let's take some very, very modest skeleton like the empty skeleton. Okay, and so like I'm studying nothing. Like they're not going to be, just one second, they're not going to be like any brains at all. And then I could like cone that off and get maybe the empty set or something. Okay, so you can always do that, but of course, the only reason this will be interesting is, as you say, if you have some.
So because skeleton doesn't mean that there's some kind of definition if you're that way.
It probably should. It probably should. Okay. It's not going to matter. So like it, the case that always guides me is this case of conormals in a in a cotangent bundle. So when we study things like branes or sheaves, we don't need to study all the branes or all the sheaves. We can study only ones that are supported even on some locus that's not homotopy equivalent. So it doesn't really matter, but probably for comfort, then I'm happy to put in your assumption. Okay, so I hope people see then that the Landau-Ginsburg model is roughly a kind of inductive scheme for taking a pair, say, of a symplectic manifold with a skeleton in it and constructing a new symplectic manifold and skeleton of a higher dimension. That's kind of what I want as the takeaway. So I want to do a specific example of this that will be the main example to calculate later in the talk, which is the following. So let's take, so I don't know what to call this, so the example of the example. So let's take, again, n equals Cn, and then W is the superpotential, it's the product of the coordinates. Okay. So this is kind of the first time you encounter something that's not, this is the first, not only not Morse function, but a function that doesn't have isolated critical points. So it's not sort of straightforward to perturb it to a Morse function. You actually need to, in some sense, go beyond what you already know how to do. Okay, so let me just remind you of the geometry of this picture. So this picture, there's one critical value. 0 is the only critical value. Okay, so here's 0. And now let's take the real line, okay, and look at, say, the point 1. And the fiber above 1, I'm calling F regular, the fiber above 1 is just T star T to the n minus 1. So there it is. Diffeomorphic to the cotangent bundle of an n minus 1 torus. Okay. And now inside of here, there are a lot of interesting skeleton that you could possibly study. So the kind of smallest one maybe that you would want to study, playing by the rules of it being kind of homotopy equivalent, would be the 0 section. So there are kind of two examples that I could have in mind. One is lambda equals Tn minus 1 itself, or I could have in mind, more generally, lambda equals T star of some stratification, Tn minus 1. Okay, so these are kind of, if you take those two pictures and you bring them down into here, those are the two kinds of things I could have in mind. Okay? Literally, when n equals 2, T star T is that picture, and I'm happy if you take those two or anything of this ilk. Okay? And now I don't want to spend too much time trying to explain what happens, but the fiber above here is all the coordinate planes, and there's a way in which you can take a limit of this and construct a skeleton in the whole space. Okay? So in the case where the skeleton is just this compact torus, this is the lambda regular. This is the kind of skeleton, the regular fiber. In this first case, what you'll see is that lambda just equals, of course, the cone over Tn minus 1. Okay? In this case, it's a little bit harder to describe because there are parts that limit away from 0, but let me just sort of ask you to imagine that you can do this kind of construction. Okay, so that's the kind of, what time did I start? 20 minutes, page 1 of 5. Beyond or Eric? Okay, so all right, that's the geometric setup I want to be in. So when we say we're going to be studying a symplectic manifold with a skeleton, I mean this situation. So exact symplectic with a conic skeleton, or maybe you think of everything as contact with a Legendrian. And in particular, I want to have in mind this Landau-Ginsburg model as our favorite example. Okay? So now the question is, what do I want to do with this? And of course, all right, you all know this subject better than I do. I want to study the A model of this situation. Okay? So my next slide, I don't know, my next thing to tell you is a little bit about what I want you to think when I say A model. Okay? So, are there questions or comments? To make these. Okay, so A model. Okay, so the challenge you're a symplectic geometer or interested in mirror symmetry, is to calculate the A model in some shape or form, hopefully showing it's equivalent to some easier B model, but in any case, to calculate the A model in this situation. So I'll write A model of M lambda. Okay, so there are a lot of different things that we can mean mathematically by the A model. I think even in physics there is not agreement on exactly what we mean by the A model. But let me list some of them for you and then discuss. Somehow the point of the talk is I'd like to add one more to the list. Okay? So in the spirit of Bernd's talk, I'd like to kind of find a version of the A model that's combinatorial. It doesn't involve some of the more challenging aspects of the symplectic geometry. Okay, so let me give you or remind you of some alternative realizations. Okay, and now I should say from the start that the kind of equivalence between these alternative realizations is, of course, its own kind of interesting research subject that we should all engage in, and it'll no doubt lead to lots of, crisper understanding of what's going on. But I don't know that anything I'm going to, any of these alternative realizations are known to be equivalent. I'm just going to tell you them, and in 10 years we'll have another conference and we'll all know they're equivalent or something. Okay, so here they are. So the first and the kind of lingua franca of this conference is Fukaya categories. Okay, so here already there's some choices to make, and there are kind of two versions among others, but two natural versions that one can associate when one has a setup like this. So on the one hand, there's what people typically call the wrapped Fukaya category, or partially wrapped. Is this the right notation? W? Okay, partially wrapped. I'm not going to tell you what these things are except just to name them, so if you want to learn about them, you can ask people who are here and experts, or people even who they were named after. So wrapped. Partially wrapped is here. So it's not, well, okay. It's one of my goals is to I don't really understand how to think about these things very well, and so one of my goals when I got interested in this was to find alternative ways to think about these things. Okay, so the other is what you might call Fukaya-Seidel category of M. So this is also what people call the kind of infinitesimal Fukaya category. Okay, so I'm not going to tell you what they are, except just to remind you of the key idea, which is that when you look at a symplectic manifold with a skeleton, you have two choices of what kinds of Lagrangian submanifolds to study. Okay? And those two choices are reflected in these two categories. On the one hand, in the partially wrapped Fukaya category, you can look at branes that run transverse to the skeleton. Okay? In the infinitesimal or Fukaya-Seidel category, you can look at branes that run near to the Lagrangian. Okay? And these are kind of like dual theories. I mean, I say kind of, I think they're now developing theorems to this effect. These are dual theories that should be thought of as like homology and cohomology, or coherent and perfect.
Transverse.
Sorry?
You really mean transverse?
I really meant transverse. So, you look bothered, so I'm happy to pause. But yeah. So, I mean, you should think, well, okay, there's lots of analogies, functions, distributions. Anyway, there are these two theories that the thing I want to emphasize is that the role of the skeleton is to somehow describe to you what Lagrangians you study and how they interact with each other. Okay. I think that's the last time I'm going to talk about Fukaya categories today, so we'll, shoot your fire now or hold it for later. Okay. Okay, so the second is something we heard in Eric's talk, which I don't know if we literally heard these words, but microlocal sheaves is something else we can define given this kind of a data, the symplectic manifold and the skeleton, and people might denote this. I don't know. There's lots of very technical looking notation out there, but this is the notation I like. So sheaves with maybe singular support in some conic Lagrangian, the cotangent bundle, is a typical thing to study, but here I'm studying sheaves that are micro-supported along this Lagrangian inside this manifold. Yeah, so it should be... Okay, yeah, so I am going to insist for this talk so there are two ways to interpret your question. So I'm very, very happy with everything being conic. Okay? So if things were not conic, someone else might be able to kind of explain a story to you. What I at least think you will need in order to kind of really make contact with what's here is you'll at least need your Lagrangian skeleton to be exact. I mean, you'll at least need to locally, or you'll need to be able to lift it to a Legendrian. If you can't lift it to a Legendrian, they'll be kind of... Oh, yeah, yeah. I mean, the whole point of the skeleton is you paid the price of singularities, but made the, I don't know, benefit of like having Lagrangian rather than singularities. Yeah, so I should say, like, I'm not going to spend much time trying to explain what this is, because in part my goal of this talk is to give you a realization that doesn't involve any of the kind of deep stories here. So like this, well, anyway, there's a, the standard reference is Kashiwara Shapiro's book, and it's a very intricate and beautiful theory. It's primarily a theory in topology, although its kind of genesis was PDE. Okay? Just like one could say this is a theory in analysis or geometry, depending on how you like to think about what you're doing. This is kind of in topology or PDE, depending on how you like to think about what you're doing. Okay, so let me just make a comment about what I see as the benefits and the drawbacks of these two definitions. So the benefit of this definition is that it's kind of completely intuitive. Okay, so when I draw a Lagrangian submanifold, like there it is, and I like know exactly if it's kind of wrapping that way or if it's moving this way. So it's completely intuitive, but of course we all know that this has a kind of a serious technical foundation that you need to struggle with. Okay? So this one I would say is kind of intuitive but technical. This one, on the other hand, has like a huge functoriality package. So you can do lots of constructions in this setting, but it's very opaque what you're doing. Okay, so this is not kind of intuitive, but on the other hand, it's kind of very easy to work with. Okay, so if your game is to prove something, this is going to be like a much easier tool. But if your game is to understand what the heck you're doing, this is probably worse. Okay. So let me, I was going to also mention modules over deformation quantizations, but Maxime has already left, and I don't need to tell Jan what he knows better than me. There's also Riemann-Hilbert, where you can think about these things in terms of modules over deformation quantizations. Okay? So I think I just won't put that up because... Yeah, you know. So I'm giving a 30-minute talk to a general audience on Monday. Berkeley, I guess there's the Breakthrough Prize will be announced. I don't know if anyone has heard who's won it. I guess none of us. So anyway, so I'm giving a 30-minute talk, and Maxime came up to me and apologized that he missed my talk today, and asked if I would give the same talk. Okay, so now let me, speaking of Maxime, let me put up a conjecture that he made, which is the following. So in this community, it certainly is due to Maxime, such a conjecture, but I was a student of McPherson, and he was certainly thinking about this kind of a question in this context when I was a student and long before. So I also just want to respect him, McPherson's program, which was that he was very interested. He was interested in how to think about things like microlocal perverse sheaves in a kind of more combinatorial way. Okay, so what the conjecture is that there should be another route to this. There should be a purely combinatorial route to this category. Combinatorial approach to this kind of quantum category. Okay, so let me make that slightly more precise, because you could say, okay, I don't know, the Kaya category is nicely combinatorial, so let me just make it a little bit more precise. So if I give you this pair, m and then lambda, so I give you this situation, you would like to associate to it a sheaf of categories, say, I don't know, lambda, okay? So a sheaf of categories, sheaf or maybe co-sheaf, depending on how you set things up, sheaf of categories. I should say all categories are enhanced, there'd be G or A infinity and so on. And you would like that this global category to be the global sections. Okay, so you would like that the A model equals the global sections. Okay, so the way I formulated it, microlocal sheaves does the trick in the sense that microlocal sheaves, because they're sheaves and local and so on, they already are a kind of a sheaf of categories. But as I said, they're kind of completely opaque. So if you ask someone to like understand a category of microlocal sheaves, it's very, very challenging. I mean, it's like calculating a Fukaya category. It's not kind of easy. Okay, so what I'm going to explain to you is a kind of solution to this problem, or I said a solution. I would conjecture that it's a kind of an efficient solution in a sense, but let me at least say that it is a solution. Okay, so I'd like to just give you an example first before I start to tell you about the solution. So here's an example. So let's go back to our Riemann surface with its skeleton. Okay, so let's go back to M equals sigma, some punctured Riemann surface. And one thing that's useful about this context is the answers are well known and easy to calculate. So no matter what model you use, finding out what you see here is a kind of not a mystery. So it's easy to kind of figure out what the answer should be and then try to engineer what you're doing. So let me just draw a local picture. So following Eric's tradition of local pictures being dotted lenses, dashed lenses. So let's say you have this ribbon graph. So lambda is a ribbon. Lambda is a ribbon graph. Okay. So locally it looks something like this. Okay, it has some spokes. So then I think most experts in the subject will know that what you're supposed to assign to this small thing is the modules, say finite dimensional modules, over the quiver with the number of nodes being one less than the number of nodes here. So if this is kind of n spokes, then you should assign modules over the a n minus 1 quiver. So n minus 1 nodes. So a n minus 1 quiver. Okay, so this is a kind of beautiful solution that then allows you to calculate, if you're interested in the Fukaya category of microlocal sheaves along a Riemann surface on a skeleton, you can take this answer locally and glue it together and get an answer in a finite amount of time. So you never have to deal with, I mean, the first Fukaya categories involve some transcendental constructions, and microlocal sheaves involve also transcendental constructions. But anyway, this gives you a kind of completely finitary approach. Okay, so what we want in some sense is an analog of this picture. Okay, so let me put up the strategy, sort of the general strategy. Okay, so well, we have to start the idea that we want to associate to, say, a Lagrangian singularity. So now I'm going to just think locally. Okay, so I'm going to think that I'm in this local situation. So I have a Lagrangian singularity, and I want to associate to it some category. Okay, so some quantum category. Okay, so the strategy that we're going to follow is the following. We're going to deform the Lagrangian singularity. Okay, so we're going to keep m the same, but we're going to deform the Lagrangian singularity, or deform, to a new kind of singularity that has, I mean, a new Lagrangian. So this is going to be a Lagrangian with what you might call stable singularities. Meaning that, in some sense, you can't do better. Like, these are going to be the singularities that are generic if you play this game. Okay? And then, from here, once we have stable singularities, like, let me just mention an analogy. So, like, a function with stable singularities is a Morse function. So once we have a Morse function, calculating something like cohomology becomes a kind of combinatorial game in some sense. So once we have stable singularities, this should be a kind of a combinatorial assignment.
Putting assign to lambda and then to this just be the same, or?
Yeah, so okay, so that's the key. All right, so the Mohammed has incisively pointed out the key idea, and then or key challenge here. So the key challenge here is, what do I mean by deform? Because of course I want not to change the answer. Okay, so what I'll add to this is the word non-characteristic. Non-characteristic, which is just a word, but it's a placeholder for the moment. I'll explain soon enough. It's a placeholder for the idea that whatever we do here should not change the category. Okay, so that's going to constrain tremendously what kinds of deformations we can consider. There are very easy ways to deform Lagrangians to easier things, but many of them will change the category. Okay, so we want to make sure we don't change the category. So I'll come back to that, but this is the kind of setup. So the two things that I want to explain in the next 10 minutes, what time? I started 30 after. What's that? Okay, so what I'd like to explain in the next 10 minutes is this non-characteristic, and then what I mean by these kind of stable singularities. Okay, so let me just say, rather than writing, or I'll just write something very briefly, that there are two analogies that I have found very useful in thinking about this, and that help organize what's going on. And I mentioned one of them, so the two analogies that I think are worth keeping in mind are Morse theory, where you play a similar game. I mean, in fact, Morse theory can be thought of as some special case of this game. And then the second is resolutions of singularities in algebraic geometry. So this is much, much more deep than what's here or here. But in any case, what's the game resolutions of when you play resolutions of singularities? You start with a divisor, and then you blow it up to have a normal crossing divisor. And then you do things like define mixed Hodge structures and so on purely combinatorially, using the fact that you have a normal crossing divisor. Okay? So somehow, if you just start with a general divisor and try to define a mixed Hodge structure, that's pretty serious work. But you, in any case, use something like this to reduce your geometry to combinatorics. Okay, so let me state now. Yeah.
Beyond the resolution of singularities, is that just an analogy, or will you make it more?
No, in fact, the way we're going to deform these is in a sense by doing some kind of real blow-ups. So it's more than an analogy. It's just that because we're working in topology rather than in algebraic geometry, we have much more flexibility, and so it'll be much easier to resolve things. Okay, so somehow the difference is in topology, you can talk about things to kind of not just to infinitesimal order, but you can actually like go out epsilon from where you stand, whereas in algebraic geometry you can't do that. Okay, so before Tim needs to catch a train, I'm going to state a theorem. It'll still be vague because I haven't formulated everything, but this is the main theorem, and then I hope to get to some applications. Here's the main theorem. Okay, so every Lagrangian singularity, again I mean exact and so on, but Lagrangian singularity, and inside M admits a deformation, or really a non-characteristic deformation, to Lagrangian M lambda tilde with what are called arboreal singularities. Okay, so the two things that I want to explain are the non-characteristic and arboreal singularities.
Lagrangian singularity, do you have any restriction? This kind of singular Lagrangians?
I mean, as long as you play within a reasonable setting like sub-analytic, or, I mean, I want to be in a setting where I can talk about like Whitney stratifications and things like that. Yeah.
Sub-analytic.
Yeah, I don't, yeah, I mean, but it's kind of very, very sub-analytic is probably the biggest. So these kind of tame geometry.
So sub-analytic set whose top strata is the Lagrangian.
Yeah, sorry, I mean, I skipped like the precise definitions, but that's right. So I would look at a sub-analytic set that for any Whitney stratification that you take, it's the closure of its top strata. Its top strata are Lagrangian with the right dimension.
Okay.
Yeah. So that's what I mean. Okay. And I should say, if you start with something that happens to be like algebraic, or produce something algebraic, anyway, it's kind of a bit of a universal paradigm. Okay, so So the first thing I wanted to address is what are arboreal singularities. Okay, so let me just try to, let me first just tell you a couple of examples, and then I'll give you a definition. So one thing that's amazing about this story, I think, is that it's really elementary. So I'm going to tell you what these singularities are. I'm not, it's not like some abstract thing. It's going to be very, very concrete. Okay, so in dimension 0, there's only one. It's a point. So in codimension 0, every Lagrangian is modeled on a point. Okay? So in dimension equals to 1, the stable singularities are trivalent trees. Okay, this is something we all know, that we can move graphs around. In dimension equals 2, there's also only one, which looks like the following. So those who are tropicalists, you'll recognize this kind of a picture. Okay, so what I've tried to draw is like 3 planes kind of intersecting in a kind of transverse arrangement. Okay? So this is a 2-dimensional Lagrangian, and this is, okay, now when you get up to dimension 3, there start to be more. So let me tell you now the general story. Okay? So the general story is that for each tree, so they're called arboreal singularities because they're indexed by trees. Okay, so if T is a tree, so what's a tree? It's some, I don't know, finite acyclic graph, okay, non-empty. So to T a tree, you can assign something like this that I'll call the arboreal singularity, and its dimension will be, dimension of LT will be equal to 1 less than the number of vertices of the tree. Okay? So if you take a tree as just a single point, you get this guy. So maybe just let me, so this guy T equals just a point. This guy T equals this. And this guy T equals this. And you'll notice that I've drawn all trees now that have 1, 2, or 3 vertices. Okay, when I get to trees with 4 vertices, there's more than 1. And that's why I haven't continued. Okay, so let me tell you what these are. So there are 2 ways to tell you. All right, I'll try to do both. Okay, so the first way is as a kind of a gluing. So I'm not going to, I should say I'm not going to tell you what they are as Lagrangians. I'm just going to tell you topologically, because I just don't have time. Okay, so telling you what they are as Lagrangians would just take a little bit more time.
Okay. These are half planes, this is not symmetric.
So you should think of this as kind of just a local model. So this is like a plane, and then
2 half planes.
and then a half plane comes like this, a half plane comes from the floor, and their interaction is kind of transient.
It's okay.
Isn't that a tropical hyperplane? No, it's not a tropical hyperplane. But maybe after the talk you'll set me straight. Okay, so so let me tell you what these are. So I'll tell you in 2 ways. So first as a kind of gluing. Okay. So the first thing we're going to do is we just take a union of all nodes in the tree. Okay. So here's a node alpha of the tree. Okay. We'll take a union over all alpha, and what we'll do is we'll look at functions on the tree that are not defined at alpha. So we'll look at functions on the tree minus alpha. Okay? So this has the right dimension. This is 1 less dimension than the number of nodes. Okay? So it's just equal to r to some n, where n is this. Okay, and now I'm going to divide out by some gluing. So let me tell you what the gluing is. So the gluing is anytime I see an edge, okay, so like this edge, alpha and beta, I'm going to glue RT minus alpha to R, well, I don't know how to write gluing, RT to the beta in the following way. So RT to the alpha has coordinates x beta and then x gamma, where gamma is not alpha or beta. So gamma is not alpha or beta. So I don't know if people can see. Here, so gamma is not alpha or beta. Okay, and this guy has coordinates x alpha and x gamma. Okay, and I ask that these two be the same if they're greater than or equal to 0, and these guys. Okay, so the picture, if you were to go back here, what you would see is I would be drawing for alpha and beta. I would be drawing this line and this line, and then gluing them along the. Okay, so that's something now you can go home and glue. Go home and do glue, I don't know. But there's an even kind of more elementary thing I can say, which is the following. So maybe let me try to do it up here. So associated to a tree is a natural poset. So associated to a tree is a natural poset. Let's call it P sub tree. So what is it? It's the poset of all correspondences of trees. So you look at a subtree, S, and a quotient tree, Q. Okay, and there's a natural poset structure on such things. Okay? You think of them as correspondences, and if you can make one as a composition of two, then that defines the poset structure. Okay, so this is a poset, and let me just tell you that this is the geometric realization of the poset. Okay, so all you need to know is the tree, you make the poset, and then you take its geometric realization, and you get this space. Okay, so a computer can process this. Okay, so that's, I mean, I want to say more, but I think in the name of time, I'll just now tell you what I mean by non-characteristic deformation, or at least give you some ideas, okay? So, I feel like I'm going very, very quickly, but I'd be happy to stop for a question. What's that? Oh, great, okay. Yeah, I'm midway through page 3. Okay, so, yeah, okay, so what are non-characteristic deformations? Okay, so of course Mohammed already said what we really want. So the outcome, whatever it is, the desired outcome has got to be that the A model doesn't change. When we do this game, the A model shouldn't change. So the form of the A model that when I say this theorem is true, non-characteristic deformations, what it's proof for is microlocal sheaves. So microlocal sheaves here are canonically the same as microlocal sheaves on this deforming guy. Okay. And now let me just state one other theorem. So let me give you a core geometric idea. I don't know, I'm trying to do too many things at once. Core geometric idea. So what you want to do, so those who have thought about something like this will know that what you want to do, say in the symplectic setting, is you definitely do not want to introduce new disks. Okay? So you do not want any new disks. Okay? So of course microlocal sheaves don't know anything about disks, so that's not sort of what's used here. But let's just continue to translate this. In the contact setting, what you want are no new reed chords, which is still not kind of close enough to traditional topology to make sense or to be easy to work with. But if you go all the way down to a kind of front projection, then what you want are no new geodesics. So let me give you one example of a kind of deformation that you should not do. To have something in mind that this is not kind of empty.
Right, and front projection means you imagine you can present on the projecting.
That's right, you locally, I mean, this whole story I'm telling you is about a germ of a, I mean, for the moment it's about a singularity. And so you think of that, you just pick some polarization, do a front projection. Yeah, okay, so here's a non-example. So let's say you started with this picture. So this is a picture inside R2 now. This is not a symplectic picture. This is a kind of front projection picture. Okay? So to follow Eric's talk, you would draw, I don't know, little hairs along your curves to convey that the Legendrian that projected here lived sort of in that co-direction. Okay? So if you were to look upstairs, you would see something like six spokes. Did I draw 6 spokes? 6 spokes, okay? So this is like, this is, I don't know, L, and then this is its front projection, I don't know, H hyperspace. Okay? So this is the Lagrangian that you're dealing with. This is its front projection, okay? And there's 7 spokes. Is that why everyone's laughing? Because there's 6 spikes? Okay? All right, so here's something you don't want to do, but you might think that it's reasonable. You might think it's perfectly reasonable to take these two parabolas and move them like this. Okay? So that looks like a reasonable way to kind of make the singularity here easier. if you haven't thought about symplectic geometry as a homotopy equivalence, everything's fine. But what you'll end up doing if you do this up here is also looks kind of reasonable. You'll deform this to something that has, say, all right, yeah, my counting is bad. It'll have, some spikes here, some spikes here. But what will be wrong is that these spikes have a kind of a cyclic order in symplectic geometry, and you will have disrupted that cyclic order. Okay? If you do this kind of thing, you'll have disrupted the cyclic order, and this won't be true. Okay? So don't do this. I'm not telling you how to prove the theorem or anything. I'm just telling you that there's kind of serious pitfalls if you just start to kind of deform without thinking about keeping things constant. Okay, so the last thing I'd like to state before doing an example is a kind of companion theorem, which makes this kind of first theorem useful. So, stated here. So a companion theorem is the following. So, let's see where I skipped it before. So the companion theorem says that if you do look at microlocal sheaves on this arboreal singularity, okay, so I look at one of the singularities that we've constructed here, and I look at microlocal sheaves on it, that this will in fact be equivalent to finite dimensional modules over the tree, where I pick any direction you like of the tree. Okay? So these trees have the property that there are kinds of special types of quivers, if you like, and there are theorems in quiver theory that tell you that picking any different orientations will still give you a derived equivalence. And you should think that roughly orienting the tree is like the same thing as polarizing M, the symplectic manifold. Okay, so polarizing means kind of picking a kind of Lagrangian vibration that allows you to calculate things. So the singularity is kind of invariant. It doesn't care about how you thought of the symplectic manifold, but if you want to actually calculate what it has, you need to break symmetry and you need to polarize, and then you get a specific tree. Okay, so between these two theorems, you can now go and calculate. I mean, let me just say, that theorem's an algorithm. It's not like resolution of singularities in its depth, but if you give me a singularity, I can go home and I can deform it. Okay? So it means that between these two theorems, I can, in principle, calculate microlocal sheaves on any kind of Lagrangian skeleton. So let me do a sample calculation, and then I think I'll quit. Questions? It'll be locally equivalent. So what can happen is, of course, you can deform and introduce a lot of interesting global topology. Like if I take a singularity of a function on a manifold, that's not Morse, but I deform it, I might pick up 28 Morse critical points with very interesting interactions that you'll have to live with. So what I'm telling you here is if you pick a very, very singular skeleton and you deform it, you'll get a nearby Lagrangian, and locally on that Lagrangian, it'll look like a quiver calculator. That's right. So let me just say a couple of, I'm going to repeat what Jan just said. So in the case of a graph on a surface, this AN story was the kind of a beautiful solution to what is the local model. And so this is a kind of replacement in higher dimensions for that. Another way to think about this is you can decide that these are not theorems but definitions. So you can decide that the definition of the A model is you take your Lagrangian, you deform it to having arboreal singularities, and then you take quiver. You don't even need to specify coefficients. You just take that quiver. And okay, and now the same theory tells you that it won't depend how you deformed and so on. And so that could be, you can take this as a kind of definition rather. I mean, this is kind of the spirit of Bernstock. You could take this kind of as a definition rather than.
So to give a definition, you do the same tree or trees?
No, you can deform and get radically different Lagrangians with very different singularities. So you can think of it like Morse theory. Like you take a function like x to the, I don't know, well, I guess in one variable you always get. But you get the idea. You take a very high singularity and you deform it. You and I might get very, very different. I mean, some things have to be constant because this theorem tells you that you and I will get the same answer. Because microlocal sheaves on the original thing makes sense. It's kind of difficult to calculate, but it makes sense. So, I mean, this is like in Eric's talk where he said, okay, I deform over here, I calculate, deform over here, I calculate, and in the middle there's something that makes sense, but it's not combinatorial. So that's the same concept. Okay, so let me just tell you a sample calculation in the last 2, 3 minutes. 4? Okay, great. Okay, so sample application. So I'm going to pick the easiest. So the easiest application I know that's kind of non-trivial in the sense that I don't know, it's hard to calculate otherwise, at least for non-experts. So, okay, so, well, let me state a general theorem. Let me just do the calculation. It's better to do it. Okay, so let's have MBC3 and W be the superpotential XYZ. And I'm trying to make things as simple as possible. Let's take inside of, what did I call it? F regular. Let's take lambda regular to just be the 2 torus. Okay? And then we'll take lambda equal to the cone over the 2 torus. Okay, so you have this picture inside C3, and this is our lambda, and now we want to calculate microlocal sheaves along lambda. Okay? And the answer is one that this community knows very well, but in any case, it's mirror to coherent sheaves. Depending on how you define microlocal sheaves, if you really go and look in the standard references, you'll just get the torsion modules, but that's not a big deal, on P1 minus 3 points. And I'd like to explain to you how to do this calculation. So somehow, I probably should have done this lecture in reverse order, so you can forget everything I've done up to now, and I'm just going to explain to you how to do this calculation. What you'll see, I think, is a kind of very beautiful, core geometric idea. Okay. So I'm going to prove this theorem for you without giving you any of the kind of why it's true, but I'm just going to go through some steps. Okay. So the first thing is, of course, what am I going to do? I'm going to arborealize. I don't know if that's arborealize, but anyway, Eric and his collaborators somehow like this word. So arborealize. I'm going to take lambda and I'm going to take it to some lambda tilde. Okay. So let me sort of just draw a cartoon for what happens here. So what happens when you do this, when you follow the kind of algorithm, is you'll see the following. You'll see a ball, a 3-ball, right? This is a 3-dimensional Lagrangian. You'll see a 3-ball, and then you'll see the rest of the cone, but the limit of the cone is some complicated subset inside the 3-ball. Okay? So inside the 3-ball, there's some surface, we call it S. Okay, and this is the picture of lambda tilde. So lambda tilde consists of 2 irreducible components. It consists of a closed ball and then this kind of thing. Okay, so by the way, someone could complain at this point that this ball has boundary, and that's a different kind of singularity. And they're right. I should at some point explain what the kind of degenerate arboreal singularities are, but I think it's not worth going into now. Okay, so here's the Lagrangian now that we're going to study. And let me tell you what this surface looks like. So now let's draw a picture of the 3-ball here, and let me tell you what the surface looks like. So you draw a tetrahedron. Okay? And this tetrahedron is going to be, the 2 torus is going to map to it by the usual Weierstrass map. Okay, so let me write 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is T2, this looks like S2, and there's a usual kind of ramified double cover of this 2 torus where I've labeled these faces to convey that they correspond to, I don't know, 1, 2, 3, 4 faces of the simplex. Okay? Now I'm going to go in and I'm going to put pluses and minuses in an alternating fashion. Plus, minus, plus, minus, plus, minus, minus, plus, okay? And what these pluses and minuses are going to tell you is when you look at the 2 faces that have, say, 1 on them, instead of mapping them both to 1, make the plus 1 a little bit farther from the origin, and the minus 1 a little bit closer to the origin. So what you're going to get is, rather than a double cover, you're going to get an immersion. Okay? So you're going to get an immersion. It's hard to draw. You should think of this as like a pillow on each, I don't know, on each face. So you get a kind of immersion away from, I don't know, ramified immersion. I don't know. 2 words. Anyway, ramified immersion away from the, the 4 points that go to the 4. Okay? And now the calculation is very easy. All right, so this is not, all right, so one can continue to arborealize this and make it really simple, but let me just tell you the answer because I'm out of time. What you'll see, if you now continue, is you'll end up finding a vector space that goes into the middle of this simplex. This is like in Eric's talk. I mean, Eric had pictures like this in his talk. He had, a picture 1 dimension down, and he told you to put a vector space, I don't know, A, B, C, D, something. He had pictures like this. So now I put 4 vector spaces, all with a map. And each of the edges tells me that the maps from Vi plus Vj to V gives me an isomorphism. Okay? So this is the category. It's 5 vector spaces, and all of these maps give you pairwise isomorphisms. Okay, so now a good exercise for you is to show that that's the same thing as a vector space with an automorphism that does not have 1 as an eigenvalue. So you use, maybe should I do the action of Kevin's? So use one of these as the domain, one of them is the range, one of them is the graph, and the other one is the graph of the identity. Make sense? No. Should I? I'm out of time, so if anyone's interested, I'll be happy to ask me immediately, but okay, let me.
Why is that coherent sheaf in P1?
Oh, coherent sheaf on P1 is a vector space with an automorphism that doesn't have 1 as an eigenvalue.
How do you get from the twofold cover of this inversion to the picture with the vector space?
I mean, I skipped some steps, but once you're in this situation, which I kind of asked you to appeal to like Eric's talk, this is a situation that's very easy to calculate constructible sheaves. I mean, this kind of, just the fact of doing this blow-up put me in a situation where calculating constructible sheaves with a prescribed singular support is very easy. It's just this answer. It's 5 vector spaces with these joint-wise sums. And I hope I've just convinced Kevin, at least, that 5 vector spaces satisfying these conditions is a coherent sheaf. Now, depending on if the vector spaces are infinite dimensional or not, you'll either get all sheaves or distortion sheaves. But, okay, let me stop. Thanks very much.
Questions?
So,
In the abstract emission, it was the serum.
Yeah, so, of course, I mean, there's another page of, yeah, I also mentioned the abstract perverse Schober's and so on. So there's an analog of this calculation in higher dimensions, and it's more involved. I mean, not a lot more involved, but it needs some kind of more of a framework to organize what's going on. And I think that's not, now, I mean, I'm happy to talk to you later, but. Yeah. So the perverse in the word perverse Schober is not that the objects of the category in any way sit inside the heart of a T structure. It's rather that in some dreamed of 2 categorical situation, the categories themselves. So.
I mean, you have some
Yeah, so why don't we, I'm happy to talk to anyone about the actual abstract, about perverse Schobers, spherical functors, and so on. Like, I would love to talk about it, but I think, yeah.
So can you think it's a challenge to the simple geometer to define Fourier homology of the verbal singularity Lagrange manifold?
Yeah.
So that possible homology is possible with that type.
Yeah, I mean, so yeah, so sorry, so the right challenge, if you like the Fukaya category as a which we do, So, I mean, there are two steps to say seeing the equivalence of the A model with this. One is, of course, to do a local calculation. So take an arboreal singularity, write down a basis of kind of Lagrangians near it, and check that their hums are what you expect. That, form modules over a tree. That should not be too bad. Maybe Mohammed doesn't.
No.
Okay. It should be straightforward. Okay. Then, if you knew that Fukai category sheafifies for some abstract reasons, then you'd be done. You would know that this model, this is equivalent to Fukai category. So if that, that's an interpretation of your question. So if you, want to know that this is a correct model for Fukai category.
So you don't expect this kind of singular Lagrangian has a
I mean, this kind of singular Lagrangian specifies a category. Maybe you know the length.
Yeah, but maybe so would you agree to say that there is not necessarily an object of the category associated with this singular object?
That's right. The singular object is specifying the category. It's saying we're going to look at the partially wrapped category. So it has the singular Lagrangian has, as you say, a Huxley homology, which you can compare to Fukai category. But it also has a category of branes running near it. So we all know.
Yeah, I understand that.
Yeah, this picture, we all know these three.
So you don't see people except.
I don't think there's any Fleur homology here except in the most trivial sense that I can tell you for any module over one of these trees, I can draw for you a Lagrangian. And then I can tell you what the Fleur homology will be between those two Lagrangians. It'll be hums between the modules over the tree. Mohammed says that's probably even easier.
I'm glad you put that picture back up, the letter Y upside down.
Yeah, great.
You can describe how you can get it from two lines by modulating half of it. Is there any significance to the...
Right, yeah, so, that's right. So of course a better picture would be to glue these three together. So in some sense, there's two things that are in tension here. There's the natural symmetries of the problem, and then your desire to describe it in a combinatorial way. So there are descriptions, of course, you can give here, but if you include all three of these objects, you have to explain to someone that one of them is the cone over the others. And to explain that, you're going to need to use something that is sophisticated in the sense that you're going to have a non-trivial A infinity operation, a non-trivial holomorphic disk. You're going to have something in your story that's kind of not naive. But kind of a miracle, or I don't know, a nice observation is that if you remove one of them, there's no longer any relations. So it's just modules over a tree. So there's a tension here. I could have presented this story to you without trees, and then you would have had a kind of more symmetric presentation. But then to tell you what the category is, I would need to break symmetry to calculate it. Or not. I could not break symmetry, but then it wouldn't appear naturally combinatorial. It would be a little bit more challenging.
The reason I ask is because that's the picture of a witness string, open string vertex, which he treats as being associative.
I mean, yeah, this, of course, that picture is kind of, I don't know, I make no claims to that picture. I mean, the Y is, it's appeared